Hello, everyone, and welcome to your Earth Science Lecture number 20. This is on the atmosphere. This is Dr. Hurt, and we're going to be talking, like I say, today about atmosphere and getting into the part of the class that deals with weather. So we're done with kind of the rock-hard Earth and done with oceans and water. Now we're getting into the weather, climate, atmosphere, things like that. So we're going to spend 2 weeks on that. And then we're going to finish up the class with 1 week on the midnight sky, the night sky, and astronomy, and that'll be it for the class. You'll be all done. So we only have a limited number of lectures left. I think we have 25 in this class, something like that. So anyway, get right on with our material today. So, the atmosphere is that beautiful shell of gas that envelops the Earth. It's the outer shell, gaseous layer of the Earth. A lot of interesting phenomenon occur in there. Let me bolster this up here. So this is, you might know, the beautiful Aurora Borealis, which are the northern lights, right? So I'll show you a little video of the northern lights here. So there's a time-lapse video of the northern lights in I think in Sweden or perhaps Norway, somewhere in Scandinavia. So you have to be pretty far up north to watch it. Now, of course, it doesn't actually look like this when you're watching it because this is, again, time-lapsed, so you see a lot more swirling and stuff than you would in reality, but still very beautiful, very cool. So that phenomenon is brought to you by the atmosphere. Actually, it was in Iceland, not in Scandinavia. So that's brought to you by the atmosphere, by the magnetosphere, which is the magnetic field part of the atmosphere. The northern lights are generated by the solar wind, interaction of the solar winds with the magnetic field. So I think I've mentioned this before, but it's pretty crazy that without that magnetic field of Earth, you and I and all life on Earth would be absolute toast. We would be baked to death by the solar winds, by the highly ionizing cosmic radiation that comes off of the sun. It's extremely dangerous. But a lot of that those nasty rays get blocked by our beautiful magnetic field. So thank God for that. You can also see the Aurora Borealis from space as well. It's kind of cool. So there's some cool videos there too. I'm not going to show them, but anyway, what is the atmosphere? So the atmosphere is, again, that gaseous envelope or gaseous shell that surrounds our Earth that's pinned down by gravity to Earth. So all of our weather and all of our climate that we know occurs within our atmosphere. So when you see the clouds and the air, that's all part of the atmosphere. Climate is, by the way, we make a distinction between climate and weather. So climate is kind of the average weather patterns and seasonal changes, extremes, and everything included in it that we get in a particular region, whereas weather is the day-to-day atmospheric conditions that change throughout the seasons, throughout the days, etc., etc. So it includes things like temperature, air temperature, and the humidity, which is how much water content there is in the air, and also the air pressure of that day. We're going to talk about all those things over the course of the next week and a half or 2 weeks. We're going to talk about all of those aspects of weather and where it comes from. So next question we want to ask is, what is the atmosphere made out of? So you can kind of think of the atmosphere in two parts. So there's the variable part and the non-variable. Okay, so the variable part of the atmosphere are things that change, and those could be things. The biggest thing is water content, or humidity. Okay, that's the biggest variable component. But also things like carbon dioxide and CH4, that's methane. Those things change as well. They're both slowly rising over the as human industry continues. They continue to rise from burning of greenhouse gases, burning of fossil fuels. Also, another variable component is ozone, which is O3. I'll talk a little bit about that later. Non-variable components are, however, the things that stay relatively constant throughout time in our atmosphere, and the non-variable stuff is shown here. It's oxygen and nitrogen for the most part. So our atmosphere is mostly oxygen and nitrogen. That's 99% of our atmosphere in terms of the non-variable components. Water vapor, you can see, can be anywhere from 0 to 4%, though. So could exceed, it can change oxygen and nitrogen contents by diluting them if you have 4% water vapor. But my point is the non-variable aspects, mostly oxygen, nitrogen. Argon is a little bit of that, about 1%. Okay, so really our atmosphere is mostly nitrogen and oxygen, a little tiny bit of argon. You know, it's kind of amazing, as much as people are so concerned about carbon dioxide. It's kind of funny. Sometimes I ask students, what percentage of the carbon, what percentage of the atmosphere you think is carbon dioxide? They often think it's really high because they hear about it talked about in the news and things like that. It's actually extremely low when you think about it. It's only 0.037%, but it's rising, and it has some, as I mentioned before, some effects upon our climate. So I'll discuss that a little bit today. But anyway, CO2 in the atmosphere is rising. It has been rising for some time. That's just directly observed since 1960s to 1990s. Here is shown, and of course this trend continues on into the 2010s and 20s. But this has been measured directly for quite some time. You see, just here, you see 40 years of history of carbon dioxide levels, and you can see that it's seasonal, going up and down with the seasons. But you can see that there's this ongoing trend of it going up and up and up. From maybe 300 in the 1960s, about 300 parts per million, and we're getting very close to 400 parts per million already. And again, that has a lot to do with using up greenhouse gases for fuel, not only for cars, but for agriculture, for all of our industry, for especially electricity generation. Livestock can also contribute to methane, which is a not as common but also powerful greenhouse gas. But I would say definitely a strong second in concern to CO2, which is quite a bit more abundant. CO2 is about 10 times more abundant than CH4 methane in our atmosphere. So anyway, we'll talk about greenhouse gases later in this lecture. But for now, let's go on to talk a little bit about other variable components. So water vapor I mentioned ozone, O3. Okay. Another thing that's also common is something called aerosols. Aerosols, aero means air, sols means soils or maybe dust. Aerosols are not gases, but they are solid particulates. Particulates that are suspended in air. Okay, so these are things like ash, smoke, dust, sea salt, actually, that can be suspended in the atmosphere for quite a long time. Those are also a variable component of our atmosphere. So humidity, though, is probably the biggest variable component of our atmosphere. So, the atmosphere can sometimes be very dry in certain places, like the Atacama Desert, the driest place on Earth, which is there in Chile, just to the east of the Andes Mountains. So the Atacama Desert's very, very dry, very, very little moisture in the air there and in the ground. Or it could be something like a cloud forest in Costa Rica, which is extremely moist, right? In these kind of situations, you have up to 4% air, 4% humidity in the air, and as you know, that extra humidity replaces the other components. So, for example, if you have 4% humidity, it dilutes the amount of oxygen that's in the air. So that's why sometimes you feel very sluggish when you're, it's a really hot day and it's a really humid day. You know how sometimes in the summer it's like that in Corpus, and it can really kind of feel hard to breathe. You know, have you all experienced that? It almost feels hard to breathe when it's really humid out. Well, the reason for that is that the water content of the air is literally diluting the amount of oxygen that you have. So you're maybe getting 10% less oxygen than you normally would. So that's part of the reason it's a little bit difficult to breathe when it's that hot out and humid out. Aerosols, I mentioned, are these other variable components of the atmosphere. These things are all of the solid particles, so this is not gas, but solid particles that are suspended in the atmosphere. And that could be sea salt, smoke, ash, dust, pollution, you name it. This is a pretty cool false colored satellite image that shows different types of aerosols in our atmosphere. So the blue color that you see, like right here, represents sea salt. The white stuff you see represents smoke, pollution. Brown represents fine ash, dust kind of material. So you could see a lot. The Sahara Desert here off the coast of Africa really produces a lot of dust. You can see, of course, sea salt, very common in ocean areas. And over the continents in North America, you see a lot of smoke and dust, big clouds of smoke hanging over California, which anybody who lives in California knows is true. I also think it's interesting that you can literally see the incursion of Gulf of Mexico air into the eastern part of our country. This is responsible. This is the reason why it's so humid on the eastern half of our country compared to the western half. This is really neat actually, because you can literally see. Y'all see how there's almost this very stark dividing line in our country, and it's green on this side and it's dry and dusty on that side, right? So you can literally see in this picture why that is, because you can see the Gulf Coast water humidity coming right into the eastern half of the country, and that's what brings all the moisture and all of the rain that makes the eastern half of America so green, the western half so barren. So another variable component of the atmosphere that's very important is ozone, which is O3. So ozone is literally just 3 oxygens connected together. Ozone's an extremely important component of our atmosphere. As you know, the creation of ozone high in the stratosphere of our Earth is responsible for absorbing a great amount of UV light. So the sun produces a lot of UV light, ultraviolet light. When it enters the stratosphere of our which is, contains the ozone layer within our atmosphere, that ozone absorbs the UV light. It absorbs the UV light, and it protects everything underneath from those harmful UV rays. So that's why, in the 1970s and beyond, people were rather concerned about there being a hole in the ozone layer, which, I think it's funny. When I was a kid in the 90s, people used to just fret and worry and stay up at night worrying about this hole in the ozone layer. And I'm still kind of like, hey, what happened to that hole? Because, it is still there. There still is a hole in the ozone layer. It's gotten better. You can see since maybe 2011, it's reached a pinnacle. But it's kind of funny that people just kind of forgot about it, and I guess they're focused on global climate change now, and they're not worrying about the hole in the ozone layer. But it is still there. It's still a problem. So anyway, the structure of the atmosphere we're going to move on to now and talk a little bit about how the atmosphere is put together. So we have 4 layers of the atmosphere, and the most interesting layer that you need to know and that we will talk about a lot is the troposphere. That's right here. The troposphere is the bottom layer, okay? And it doesn't really go up too high, maybe about 10 kilometers it goes up. And after the troposphere, sitting on top of that is the stratosphere. So the troposphere goes about 10 kilometers up. And I want you to notice this red curve that you see, right? Let me get all the ink off this side. See this red curve right here that goes along? You can track it. That represents the temperature. So as you see, when you get up into the troposphere, it gets colder and colder and colder. See, if you move to the left, you're getting colder. If you move to the right, you're getting warmer. Then you'll notice after the tropopause, which is the barrier between the troposphere and stratosphere, it's the trend in temperature starts to change. It reverses, and things start to actually get warmed up. Does that surprise you? It actually starts to get warmer as you get into the atmosphere in the stratosphere. So, and in fact, it actually, by the time you get to the stratopause, which is the boundary between the mesosphere and the stratosphere, once you get to the stratopause, it's actually kind of relatively warm. I mean, it's still freezing, but it's not really like sub-zero Fahrenheit. It's relatively warm. So that's kind of might surprise people. The reason that it gets hotter in the stratosphere compared to the troposphere, the reason that it starts to get hotter in the stratosphere is because the stratosphere is absorbing all that UV light that's coming from the sun. So again, once you get into past the stratopause, 50 kilometers up, you go into the mesosphere, and between the mesosphere and the thermosphere is the mesopause, and in the thermosphere, things get very hot. Now, you might be kind of surprised at the temperatures they list here. I wouldn't take those too seriously. I take them with a grain of salt because the atmosphere is extremely thin at that point. You're talking about a handful of molecules in a square meter in a place like that. So it's kind of, I don't want to get into all the physics of how gases are, but it is hot because it's absorbing a lot of material, a lot of energy that's coming off of the sun, but it's not as maybe hot as it would seem, 1200 degrees Celsius per se. But anyway, the stratosphere and the troposphere are the things you really want to know. Now, you have to understand that it gets very cold very fast in the troposphere, and that starts to warm up in the stratosphere. What happens beyond there is not as important. But anyway, another thing you also need to understand about the structure of the atmosphere is that its density. Okay, the atmosphere is very dense near the bottom of it. So in the bottom half of the troposphere, the air is relatively dense, and it gets much lighter as you go up. So you can see that the molecules of air get sparser as you move up in the column of the atmosphere. Okay, most of the atmosphere is concentrated in the bottom half. So pressure changes throughout the atmosphere due to these changes in the density of the air column. Okay, so as you move through, this is showing your density. Okay, or I'm sorry, this is showing your air pressure as you go up. So air pressure changes as you go up through the atmosphere. So near the surface, the air pressure this is in millibars, by the way. It's 1,000 millibars, which is 1 bar. Okay. And as you move up through the atmosphere, it drops off very fast. So by the time you get into the stratosphere, 10 kilometers up, or actually, I'm sorry, this is 10 miles. So maybe stratosphere is even down here. This is the stratopause, right? You've lost a lot of your mass of your atmosphere and density of your atmosphere and a lot of your pressure. So you're down here maybe at near 100 millibars. You've lost 90% of your pressure by the time you get to the stratopause. Okay, just of course stratopause is far above Mount Everest, right? So anyway, that's what it's like. Pressure goes down as you go up so altitude goes up, pressure goes down. Altitude goes up, density goes down. Okay, altitude goes up in the troposphere. Altitude goes up, temperature goes down. Okay, so you should know all those different relationships. So again, it's that formation of UV light that absorbs all the energy that causes there to be a temperature increase in the stratosphere. Now, the change, a very important concept that I want to just introduce at this time, I'm not going to go into great detail about it, but just introduce it, is this concept of a lapse rate. The lapse rate is the change in temperature divided by the change in elevation or altitude. Altitude and elevation are the same thing. Okay, so that's all a lapse rate is. It's just the change in temperature with the change in elevation or altitude. So in the troposphere, where most weather occurs, the temperature generally it decreases with elevation. And the rate of temperature change with the change in elevation is the lapse rate, okay? And that has a lot of very important, what the lapse rate is, has a lot of important ramifications for what the weather will be like on a particular day. So you need to understand this whole concept of a lapse rate. We're going to get into this in lots of gory detail eventually, but right now, suffice to say, I just want to introduce the topic to you of a lapse rate. Okay, so let's take a little, so that's the atmosphere kind of in general, what it's made of, what it is, how it's structured. I want to get into a little bit about how the atmosphere is heated up, and to talk about that, we have to talk a little bit about the seasons. Now, I already talked about the seasons a little bit in the beginning, very beginning of the course, so hopefully this is going to be a little bit of kind of almost like review for you, and it should all sound a lot of it familiar. So, as you know, the Earth, we have four seasons. What causes those four seasons? Well, it's the rotation of the Earth around the sun, and it's the fact that there's a tilt to our Earth relative to the ecliptic plane. Okay, the ecliptic plane is the plane in which that contains our orbit. Okay, so our Earth orbits in the ecliptic plane. Okay, when you look at the night sky, you're going to see the sun move through the night sky, and here's kind of imagine you're looking at the sun. It's going to move through the night sky. It actually traces out, as it moves, it traces out the ecliptic plane. Okay, so you're literally looking at the ecliptic plane when you follow the trace of the sun through the sky. Now, our Earth is rotating, of course, spinning around as it goes around and revolves around the sun, and the angle of that rotation is 23.5 degrees, right? Degrees, there we go, relative to the ecliptic plane. That is the kind of basic fact that creates our seasons. So I'll explain that in a little bit later. To do one complete revolution around the sun takes 365.25 days. That is why we have a leap year, by the way, every 4 years. It's to make up for the fact that we do 0.25 rotations around the sun. It's not a perfectly whole number. So the path is nearly circular, but it's not quite. It's actually elliptical, which is kind of an oval shape. Okay, so Earth orbits within the ecliptic plane. Its spin axis is tilted 23.5 degrees relative to that flat plane. Okay, average distance to the sun from Earth is 93 million miles, but that will change. You'll see. We'll go into this a little bit of detail. That'll change throughout the year. Sometimes we're closer, sometimes we're further away. So the Earth spins on its axis once every 24 hours, orbits around the sun every 365.25 days, and it has a spin axis that points in a constant direction. And in fact, our spin axis always points towards the North Star Polaris, which is why we call it the North Star. So the spin axis is tilted 23.5 degrees from the perpendicular to the plane of the ecliptic. Okay. Now, the sun, like I said, is not precisely the center of Earth's orbit. Okay, it's actually not precisely the center of Earth's orbit. We're actually at one of the focuses of an ellipse, and that's why we are not always at the same distance from the sun. Okay, sometimes we're closer to the sun, sometimes we are further away. The point at which we are furthest away from the sun is called the aphelion. It occurs on July 4th on Independence Day, actually. So that's when we are furthest away from the sun. The perihelion, occurs on January 3rd. That's when we are closest to the sun. Now you might be thinking to yourself, July 4th, it's really hot July 4th. So why is it? It's hard for me to believe that the day we're furthest from the sun is July 4th. Now that's the reason that it's still hot on July 4th It's because, even though we're furthest away from the sun on that day, it's because our Earth is tilted towards the sun. And because it's tilted towards the sun, we're getting more direct radiation from the sun. When we're tilted away from the sun, like we would be in the southern hemisphere versus the northern hemisphere, we're going to get less direct rays. The rays are going to be spread out over a longer surface area, and then we're going to get kind of lower temperatures. Okay. So the seasons occur because Earth's axis maintains a constant orientation in space. It's always tilted 23.5 degrees with respect to the perpendicular to the plane of the ecliptic. It's always pointing towards the North Star Polaris, and this changes the amount and intensity of sunlight we receive at different latitudes over the course of the year as Earth revolves around the sun. So the changing orientation of Earth's axis to respect to the sun over the course of the year is shown right here. So when the axis, now look at our axis here. You see how the axis is pointed towards the sun. Okay? When it is pointed directly towards the sun, that is what's called the summer solstice. The summer solstice occurs on June 21st. That's when we receive the most sunlight, the longest day. It's the hottest, longest day of the year. Okay? Now, on the flip side, when our axis is pointed directly away from the sun, then that is the winter solstice, December 22nd. And that's when we have the shortest day of the year. And we also get less sunlight, less solar radiation, so we're going to have colder temperatures around that time. Now, between the summer solstice and the winter solstice, you have two equinoxes. Okay, so the equinox means equal night. So these are the 2 days in which we receive exactly 12 hours of sunlight and 12 hours of darkness. The first vernal equinox, which is the spring equinox, which happened not too long ago, is on March 21st. Okay, and you can see that it's when the Earth's axis is pointed directly perpendicular to. There's a perpendicular right angle here between the Earth's axis tilt and the direction of the sun's incoming rays. Okay, so it's not pointed towards the sun, it's not pointed away from the sun, it's pointing directly to the side of the sun. Okay, so the other equinox is on September 23rd. That's the autumnal equinox. Okay, so those are the 4 important, very important Sun-Earth geometry positions that give us the 4 seasons. Earth rotates counterclockwise. So we're going to go from winter to the vernal equinox, to the summer solstice, to the autumnal equinox, back to the winter solstice. Okay. So just a little video that might help you kind of imagine all these things. I play this one for you. So there's this nice little YouTube video that kind of maybe shows you these things a little bit more. It might be easier for you to understand watching it as a video. Okay.
For early astronomers to figure out which day of the year it was easy for early astronomers to figure out which day of the year was the longest, which day of the year was the shortest, and which days appeared equal. Welcome to Moo Math and Science, and what happens on the equinox and the solstice. Because the Earth is tilted at a 23.5 degree angle and also rotates and revolves around the sun, the length of the day varies throughout the year. During each equinox, both hemispheres receive almost equal amounts of sunlight, 12 hours of daylight and 12 hours of nighttime. The actual day in which both hemispheres receive 12 hours of sunlight and darkness is called the equinox, and usually occurs a couple days before the March equinox and a few days after the September equinox. The day of a solstice in either hemisphere has either the most sunlight of the year, which is the summer solstice, or the least sunlight of the year, which is the winter solstice, for any other place on Earth other than the equator. Does the sun always set due east and set due west? Actually, the sun rises in the east and sets in the west only 2 times a year in each hemisphere. In the northern hemisphere, on March 20th, which is the first day of spring, also called the vernal equinox, the sun rises due east. Moving forward, the sun then starts setting a little more northeast.
I think you get the idea now, so I'll stop it here. But oh, whoops! Here we go. So anyway, on the summer solstice, oh, where's my pen? I'm looking for that thing. Sorry. Oh, where'd I put it? Oh, here it is. Okay. So on the summer solstice, the subsolar point, which is the point at which the sun's rays are coming down directly overhead, the subsolar point is directly over the Tropic of Cancer in the north. During the winter solstice, it is directly overhead the Tropic of Capricorn in the south. Okay. So that's why we have the tropics at 23.5 degrees north, 25.5 degrees south. Okay. Another thing I wanted to show you that's kind of cool is that you'll see that in the Arctic and Antarctic circles, you will have days that have at least one day of 24-hour sunlight and 24-hour night. So I wanted to show you a little video. Oh, I forgot to load it, but I want to show you this little video of the midnight sun, which is pretty cool. So, whoops. Midnight sun time lapse. This isn't really the best one. Let's see. I want one where it actually follows the sun. I used to have a video that did this, and I can't find it anymore, but I'm gonna maybe make this play faster. So you can see that the sun gets very close to going down, but it doesn't quite go down, right? So there it is at its lowest point, and then it's going to rise back up again. So anyway, I used to have a better video that used to follow the sun. Let's see if I can find it. I think maybe it's this one. Yeah, you can see it gets low, but doesn't quite go under the horizon. So that's the midnight sun. And of course it sucks because on the flip side of this, during the winter here, you get 24 hours of darkness. So it's pretty, you could imagine what it's like. And you know, at the North Pole, South Pole, you would get a whole 6 months of either light or 6 months of darkness. Okay. So anyway, that's what it's like. I think that's all I have to say about these things. By the way, the only reason I want to kind of clarify why it's warmer and colder during the different seasons. It doesn't have anything to do with it being closer or further from the sun. Okay, I mean, the amount of distance that the change in distance on average that we are from the sun changes very little. You know, it ranges between like 153 million kilometers and like 147 million kilometers, and so it's really not that big of a difference. What changes is the angle. So you could imagine if light is coming down directly, shining on a spot, that same energy is concentrated over a smaller area than if it's shining at an angle. You see that light is shining over a larger area, and so the solar energy gets spread over a larger area. So it's just that we're receiving, during the winter time, we receive less solar energy per square foot, like per surface area. Okay. So let's talk a little bit about how the atmosphere gets heated up. So the atmosphere heats through a couple different processes. Now there's 3 ways to heat up anything, right? And those are convection, okay, conduction, and radiation, all right? Convection is when heat is transferred through a liquid or a gas by molecular circular motions. Conduction is when things are heated up by direct contact. And radiation is when you're heating something up by energy, by light energy, okay? So now, of course, we are heated up in the atmosphere by radiation from the sun. So this is showing the kind of the spectrum of radiation coming from the sun. Okay, now this is the wavelength on the bottom here, and the intensity of the sunlight over different wavelengths. Ultraviolet light, you can see, is pretty powerful, but the peak is concentrated in the visible light spectrum. However, there is a lot of infrared radiation as well, and there's other things such as even radio. It might surprise you, the sun even emits radio waves, TV waves, even releases microwaves like what is inside your microwave oven. Okay, but a lot of infrared radiation as well. But the highest peak is visible light. So a lot of solar energy, 44% of solar energy is visible light. Okay, so that light that comes in, what happens to it? So here's the incoming solar radiation. About half of it is absorbed at the surface. 20% of it is absorbed by clouds and atmosphere, and the rest is reflected. Okay, a lot of it's reflected by the clouds, reflected by the atmosphere, reflected off the surface. Okay, the amount of radiation that is reflected back into space is called albedo. Okay, now when the atmosphere absorbs more sunlight, you're going to increase the temperature of the Earth. So this is what's happening with greenhouse gases. Greenhouse gases are very good absorbers of infrared radiation. So let me explain something here. The light that comes into Earth is mostly here. Let me do this with kind of a yellow pen. Whoops, I meant to pick yellow. Okay, the light that comes in from the sun is mostly visible light. Now, when that visible light is absorbed at the surface, okay, it's absorbed at the surface of Earth, it's going to be released and re-emitted as IR, infrared light. Okay, so there's going to be absorption of the visible light at the surface, and then that surface is going to re-radiate that energy as IR, infrared. Okay. So, have you ever just kind of stood close to somebody? Not touching them, but just very close to them. And without touching them, you can feel the heat coming off their body, right? Same thing with Earth, right? You can feel, like for example, on a hot summer night, you know, after in the summertime when the Earth has absorbed a lot of, here in Corpus Christi, we've absorbed a lot of sunlight, you can feel the heat coming off the ground, you know? Like I know, like, gosh, I walk out barefoot out onto my concrete driveway at nighttime in the summer. It's still hot, you know, it still like burns my feet going out there. That's the IR. That's the infrared radiation coming off of the ground. You can't see it. It's invisible. But you can feel it. So IR radiation is invisible. You can't see it, but you can feel it. Okay, it feels like heat coming off. So it's radiating. Earth re-radiates that IR. The thing about greenhouse gases, so I'm going to put in green, maybe I'll put greenhouse gas. Greenhouse gases, so the visible light goes right through them. Okay, visible light goes right through greenhouse gas. But the IR gets trapped. The IR hits that greenhouse gas and it can't escape. That's the problem with IR. That's the problem with greenhouse gases like CO2 and CH4. And also, by the way, the most common greenhouse gas, a lot of people forget to tell you this, but the most common greenhouse gas, you know what it is? I'll write it out for you. The most common and most abundant greenhouse gas is H2O. It's a very powerful greenhouse gas. CO2 is another one. CH4 is another one. But the greenhouse gas that's most powerful and most abundant is actually H2O. Now, have you ever, I'm sure you know, during the summer, you actually kind of get a greenhouse effect in the summer in your car. So you know that light comes into your car. During the summer, you're sitting out in the parking lot at the mall. You come out of the mall after a couple hours of shopping. You get in your car and it feels like an oven. It's hotter than outside. It feels like an oven. Why? The reason is that the visible light from the sun can get in through the windows, but the IR radiation, it gets absorbed and it tries to cool down by releasing IR, but the IR cannot get through the glass because glass is also, it absorbs IR. Okay, I want to show you kind of a cool video. I bet a lot of you didn't realize this, but I'll try to prep you for this. But so some materials that absorb visible light don't absorb IR light, and some materials that absorb IR light don't absorb visible light. So what this means is that some things are opaque, you can't see through them in visible light, but you can see through them with IR light. Just like X-rays, right? You can't see your bones in your body, but with X-ray vision you can. Same thing with IR. With visible light you can't see through it, but with IR you can. And vice versa, some things you can see through with visible light, but you can't see through it with IR. So I'll show you a little video. It's pretty cool. I'm going to kind of skip through it, but I'll show you some of these things.
You've seen some military footage that looks like this.
So probably a lot of you have seen military footage like this, which is an IR camera.
Infrared imagery. And what it does is it essentially gives you the superpower to see things that you wouldn't normally see. So for instance, your eyes, they normally see in the visible part of the spectrum, which you can see here, so you see the colors and everything.
Now take a look at this guy's glasses. Do you notice how his eyes look darker because of his glasses? That's because the IR light being emanating from his face, because, you know, by the way, I don't know if you realize this, but you're emanating, radiating out IR light right now as you speak, or as I speak. It's being blocked by his glasses because glass is opaque to IR.
However,
I want to show you some other things here.
That your eyes aren't sensitive to, that you can actually see my eyes.
See how he took his glasses off? Now you can see his eyes are white compared to black.
When in reality, the perspex here actually very effectively blocks out spectrum.
Now another thing, he's going to take this trash bag. Notice in visible light, it's opaque. It means the trash bag absorbs visible light, but it's invisible or kind of invisible in infrared light. You see that?
Blocks out all of the light. However, this is polythene, and what you'll find is for the infrared, it's not quite so good at actually hiding my body heat. That is.
So another thing is glass. Take a look at. I think he's going to get a piece of glass here. Yeah, here's a piece of glass. This is pretty cool. So look, you can see him perfectly in visible light. So because visible light goes right through glass, but IR light you can't see him. He's basically blocked out.
So this would be great for hiding from infrared. Not so good for the visible.
Okay, so the idea is this, and how it applies is this. Greenhouse gases in our atmosphere, like CO2, H2O, and CH4, are very good absorbers of IR light. So what happens is that Earth tries to cool itself down by releasing IR light, but it gets absorbed and blocked by the greenhouse gases. Okay, get trapped in the atmosphere. So that's what's going on here. Now, let me see how long. I feel like I've been going on kind of a long time. No, 45 minutes, so it's not too bad. But let's move on now to, so that's kind of a basic, gives you some of the basic ideas of how Earth's atmosphere is heated up, how greenhouse gases play a role, how infrared and visible light, different spectrums of Earth's or solar radiation play a role here. But let's talk too about kind of how we map out now temperature variation over the surface of the Earth. So we map out different temperatures on Earth's surface using things called isotherms. Isotherms are lines of equal temperature. Okay, so everywhere along an isotherm, if you see an isotherm on a map, it is at the same temperature. This isotherm that I'm highlighting right here is the 0 degree isotherm. Okay, it gets colder as you go this direction into this kind of cold pocket right here. It gets hotter as you go out towards this direction. Okay, this is a map of just isotherms, average isotherms over the surface of the Earth for January versus July. You'll notice that there are some places it gets extremely cold, right? Negative 35 degrees in January, negative 50 degrees in parts of Siberia, extremely cold. Notice it never gets that cold in the southern hemisphere's July. And part of that has to do with the fact that the southern hemisphere, like I explained before, is predominantly water. So not predominant, well, it is predominantly water. Yes, it's true. It has a lot more water than the northern hemisphere, a lot less land. So that coastal kind of, remember I talked about the difference between Chicago and Seattle in one of the lecture assignments? Seattle has much more even temperatures throughout the seasons. It's the same effect that's going on. So you notice how we don't get, July is the winter time, right, for the southern hemisphere, and yet we don't get nearly as cold of temperatures as we do in the northern hemisphere. So things get a lot colder up north. Things get a lot colder. And that's because we have lots of land up north compared to the southern hemisphere. So some of the factors that influence what the average air temperature is over the surface of the Earth are as follows. Latitude is a huge one, right? So I mean, notice that as you move from, this is the equator right here. Notice as you move from the equator, obviously it gets colder, right? So as you move further north or you move further south, it gets colder. Okay, so higher the latitude, generally more cold. Okay, that's an easy one to understand. So you get close to the North Pole or the South Pole, it's going to get colder. You get closer to the equator, it's going to get warmer. Now the surface type plays a big role here too, and I showed you that a little bit with when I talked about albedos. Okay, so albedo, remember, is how much of the solar radiation is reflected off the surface. So if you have a forest, it has a different albedo than a desert, which has a different albedo than ice. So all those things, what the surface is made of and what the albedo of that surface is, plays a big role. Forests and highly vegetated areas have very low albedos. They absorb a lot of solar radiation. Ice, on the other hand, has a very high albedo, reflecting up to 90% of the radiation back into outer space. Okay, that is why, for example, if you go skiing, if you ever go skiing in a place with a lot of snow, sometimes you have to actually wear sunblock or sunglasses because the reflection of the solar radiation off the snow is so intense. Coastal versus continental settings, as I explained a few times now in this class before, coastal areas are much more mild in their seasonal extremes. Coastal settings, remember, being near the water as they are going to be influenced by that high heat capacity of the water. The water is able to kind of hold its temperature better than land. Okay, land is much more finicky and susceptible to temperature changes and variations in the temperature. Okay, so you get smaller temperature ranges by the oceans, larger temperature ranges in the continental interiors. Look, for example, there in Siberia, it's negative 50 degrees in January, whereas it's maybe 15 degrees during July. pretty balmy, really. So you got a huge swing, you know, a 65-degree temperature swing there in the interior of the continent, compared to if I go, let's say, pick a place on the coast, let's say England. You can see that in January, England is about 5 degrees, and during July, it is about 15 degrees, right? So it's only a 10-degree swing and variation of temperature between the seasons, okay? Elevation plays a big role too. A thinner atmosphere in mountains means less greenhouse gas trapping heat, generally cooler temperatures, and a larger diurnal, that's a day-night. Some people call that diurnal effect, okay? So, for example, being on top of this, high elevation cities like this place, Arequipa in the Andes, 7,500 feet above sea level, you're going to get these very high temperature extremes and generally cooler temperatures. So here's air temperature. As you go from left to right, we're going to get higher and higher and higher in elevation. You can see that as we go higher and higher and higher in elevation, average temperature goes down, okay? So again, that's due to the higher elevation, the daily temperature ranges increase, notice that, and also they're due to less greenhouse gas effects, okay? So yeah, notice how, let me erase all this stuff. Notice how the day-night temperatures here at the sea level are very small, but the day-night temperature variation up here in the mountains is huge. Look at that, very, very big, you know, going anywhere from 10 to 50 degrees, so 60 degree, huge 60 degree temperature variations. It's very big. So as you get into the mountains, okay? So as you go higher and higher in elevation, you should expect bigger temperature swings and colder temperatures on average. So those are kind of the 4 big things that affect what the air temperature in a particular place is going to be like. Again, remember, one of the reasons it gets cold as you go up in elevation due to the greenhouse gas effect being lessened, and also due to this whole lapse rate. You know, it gets colder as you go up in elevation, okay? Remember, land and water temperatures, coastal versus continental interiors. You'll notice that Topeka, Kansas has a much higher temperature extreme than San Francisco. It has much more even temperatures over the course of the months, okay? Much less seasonal variation. And that is due to it being coastal rather than in the center of a continent or continental, even though they are both at exactly 38 degrees north latitude. So just kind of talking a little bit more about surface types and how that affects temperature. Water has a very high heat capacity. It heats up slowly. The radiation also from the sun is able to penetrate deep into the water and heats up the whole water column, so that that solar radiation gets spread out through the whole depth of the water column, rather than just being a superficial feature like it is on the land. Also, heated water is able to mix with cooler water down below, and evaporation of water is able to help to cool the water down. So the long story short, it takes a long time to heat up water and change its temperature, okay? On the other hand, land has a low specific heat. It heats up quickly. Doesn't allow, the radiation can't penetrate the surface, so it's just superficial. There's no mixing of heated, hot land surface, like superficial heated land with the colder land below. You obviously can't mix the land up, and there's no evaporation. So land heats up very quickly, and it loses its heat very quickly. So those factors contribute to the vast disparity between water and land in terms of seasonal variations throughout the year. Okay, so yet another, again, factor you see here, maritime being coastal. Here's San Diego and Las Vegas. You see much larger temperature variations day in and day out throughout the course of a day. This is the diurnal effect. Okay, you see it gets cold during the night. Sorry, it gets cold at night, gets warmed up during the day, cold at night, warmed up during the day. And those diurnal temperature variations are much bigger in a place like Las Vegas, which is on the interior of a continent, versus San Diego, California, which is on the west coast. Okay, so that's all I have for you today. I hope you enjoyed the lesson, and I will talk to you next time. We're going to get continuing along talking about moisture, clouds, and precipitation.